So we're going to look at how to balance redox equations using half reactions. When we use the half reactions to balance equations, we're using the ion-electron method. Redox reactions occur when all species are in solution. The ion-electron method can be broken down into the following three steps. These are the three steps we'll be using. So we'll write out balanced oxidation and reduction half reactions. We'll then balance them so that the number of electrons produced is equal to the number of electrons consumed in the process. And then we'll add the two half reactions in a method similar to Hess's law so that we have a balanced net ionic equation for the redox reaction. So this is going to give us a reaction that is balanced for electrons, but may not be balanced for the other species in the reaction. Specifically, hydrogen and oxygen aren't always balanced after we finish balancing the electrons. So there will be some additional steps that we're going to have to complete. We're going to balance for oxygen by adding the water molecules to the solution. Now, the water molecules are already present because in solution chemistry, these are things dissolved in water. So we're just going to be using some of the water that's present to help us balance out our equation, because obviously some of the water molecules are actually being involved in the reaction. And then these redox reactions occur in one of two solutions typically, so either acidic or basic. So in the case of an acidic solution, we're going to balance for hydrogen by adding hydrogen ions to the opposite side of the reaction. So if we've got an extra couple of hydrogens on one side, we'll add a couple hydrogen ions to the other, and we'll go from there. So let's just take a look at an example here. So the very first step when we're doing these problems is to determine what's being oxidized and what's being reduced in the method we've done in class. So maybe pause the video and just take a moment to identify the oxidation and reduction numbers for these species, and then we will see who's being oxidized and who's being reduced. I just noticed one little tiny thing here. So the Cr2O7 should have a 2- charge. So that'll change oxidation numbers potentially. So pause the video now and figure out what oxidation numbers are. Okay, so I'm hoping that you were able to correctly identify the oxidation numbers and the gain and loss of electrons by the elements that were changing their oxidation number. So chromium changed from a +6 to a +3. And the carbon went from -2 to 0. Now what we're going to do now is just write down the half reactions for the two elements that changed oxidation number. So that will look something like this. Okay, now here's where we need to be careful. So in this reaction here, we know that carbon loses 2 electrons per atom. But in the oxidation half reaction, there are actually 2 carbon molecules, or 2 carbon atoms rather. So we need to be careful that the number of electrons per atom matches the number of atoms in our reaction. So there are 2 carbons, so we're going to need 4 electrons produced per atom. So it's going to lose a total of 4 electrons. Now the chromium is especially challenging in this problem. So you'll notice that we have 2 chromiums on the reactant side, only 1 on the product side. What we're trying to do here is create a balanced equation. So that means that we also need to make sure that the species that are changing oxidation numbers are also balanced. So the chromiums first, we're going to make sure that there's the correct number. So there's 2 on both sides. Now chromium is requiring 3 electrons per atom. There are 2 of them, so that's going to give us a total of 6 electrons. Okay, now this is where just general balancing comes in. So we have 4 electrons produced, 6 electrons required. Those aren't the same value, so we're going to have to find a common number for both, and the lowest common number also. So 4 and 6 both can go into 12, so we're going to multiply everything in the oxidation half reaction by 3. So now we'll have 12 electrons produced, and everything in the reduction half reaction by 2. So we're now going to have a requirement of 12 electrons, and we'll have four chromium atoms involved. So now we're going to add this reaction in a method similar to what we did in Hess's law. So we're going to take these two half reactions and combine them. So we'll have 3 ethanols reacting with 2 chromate ions or dichromate ions to produce 4 chromium ions and 3 of those. So if we take a quick look now, we will see that the number of electrons are perfectly balanced. But then when we start looking at the other atoms, we're going to have some issues. So hydrogens and oxygens currently are not balanced. So let's figure out how many hydrogens and oxygens we have on both sides. Okay, so we see that there are 14 oxygens and 18 hydrogens on the reactant side, 12 hydrogens and 6 oxygens on the product side. Now we're going to concern ourselves first with the oxygens, because when we add waters, we're also going to be adding hydrogens, so that'll distort everything. So 6 oxygens versus 14 means we're 8 short, so we're going to need to add 8 waters. Now obviously the water comes with some attached hydrogens, so we're getting an additional 16 hydrogens on this side, which will not balance with our 18 on the other side. So the total there is 28. So we're going to need to add 10 hydrogen atoms, or ions, excuse me, to the reactant side. Now, often what comes up is, where did these waters and hydrogen ions come from? The simple response is, it says up here in the question, sort of obscured right now by all this writing, but we're dealing with an acidic solution. So we have an acidic solution. Acidic solutions contain both water, which is now going to actually be a product of our reaction, and hydronium ions, which are, in this case, a reactant, but present because it's an acidic solution. So if you go on to the next example and pause the video, why don't you try the next example without looking at the solution, and check back on the solution when you're done. So just to repeat the steps, first thing you're going to do is identify what's being oxidized, what's being reduced, how many electrons per atom are involved in each of those half reactions. We're then going to make sure that the electrons that are released or lost equal the electrons that are required or gained. If they don't, we're going to pick a coefficient that allows those two values to be the same, multiply everything in the half reactions by that coefficient, add them, and then simply add waters and hydrogen ions to make sure that our oxygens and hydrogens balance. Okay, so pause the video, try the next example, and then check back. Okay, I'm hoping you got this far without too much difficulty. So I've identified that the copper is oxidized, losing 2 electrons per atom. The nitrogen in the nitric acid gets reduced, gaining 1 electron per atom. If you write down your 2 half reactions, you can see that there are 2 electrons produced, 1 electron required, so we're going to multiply everything in the reduction half reaction by 2, and then add them. Okay, then if you take those 2 half reactions and add them, you're going to get the sort of balanced chemical equation starting point that we have here. And you'll notice that there are 6 oxygens on the one side 2 hydrogens on that side as well. So the reactants have 6 hydrogens, 2 hydrogens rather, and the product side has only 4 oxygens. So the way to finish this balancing off is, if we look up in the question again, this is occurring in an acidic solution. We know it's in a solution also because of the aqueous present. The acidic part tells us that we're going to be able to add hydrogen ions to balance off the hydrogens. We're 2 oxygens short on the product side, so we'll have need of 2 waters, which will then mean that we now have 4 hydrogens along with our 6 oxygens on the product side, which we can balance off by adding 2 hydrogen ions. Now sometimes you will put hydrogens and waters on the same side. It's not always that the water's on one side and the hydrogen's on the other, but it does often work that way. But don't be alarmed if it ends up being that you have 2 and 2. All right, so we'll try some more examples tomorrow in class, and if you have any questions or concerns, of course, please ask me. All right.